Okay, good morning. Um, Today we're going to continue on the lecture on indexing. We are going to span like two lectures. Today will be the not really overview, but well, we will see a little bit on indexing. And then next week we have milestone 3. And then the week after that, we'll come back to indexing again. Yeah. All right. And as you could see, the slides are like a lot today. So we have a lot to cover. All right. And I have to say, these two lectures about indexing are probably the most difficult and challenging in terms of like you need to understand this for the exam. All right. And probably the one that you scored the least on. So, well, just a little heads up so you like pay more attention and try to understand the material. All right. Okay, so let's start with the overview of what we're going to be doing today about indexing. Before we understand how indexing works, we probably have to sort of understand the concept of how DBMS would store and access the data that we store. Let's say we create a table or some tables um, in MySQL or whatever. How do they actually store them? And we will look at I/O cost a lot, especially like in the indexing part, because we see that it's a bottleneck of like the say the CPU time is, I would say, negligible comparing to I/O. Because I/O, we need to read something from disk or write something on disk. So that would take more time. So that's the thing that we will focus on. Okay. And we will have some way for DMS to organize the data so that we try to minimize the I/O costs as much as we could. All right. And at least we're getting out of the lecture today, we have to understand what the index is and when we're going to use it and use it for what, you know, and the properties of index. And we will look at two types of main index schemes, which are tree-based index and the hash-based index, right? And how we're going to use the index to optimize the performance, given we have workloads and things like that. So this will extend to the next lecture on indexing as well. All right. And before we go on, we have to understand that when we access things, do you take OS class? Is it in the curriculum? Operating systems? Okay. All right. It's okay. But now we have to understand that the way we access the data, we cannot access bytes by bytes. We cannot say like, oh, I want to access 8 bytes or read 10 bytes from this. You cannot do that. We have to do it in chunks, like we call it in blocks or in page. Okay, so if you want to know more about these things, you can read about file system and how it's organized, like how it's physically organized as blocks on this, or in terms of operating systems, the software side, we will have very similar scheme, but we call it a page. A page could be the same size as blocks, or well, typically something like that. But the access unit is called the page. In the software's level. All right. So whenever we want to access anything on disk, we have to bring out the whole page from this. And we modify something. And then when we want to write something back, we cannot write back a few bits or bytes. We have to write back the whole page. So that's a whole deal of this thing. Okay. You have to understand the unit is go by page. Okay. But the size of the page depends on the OS. You could have smaller size page or bigger size page, and the performance could vary according to those. Okay. And the cost unit, we will call it a page IO because we have a page that could be like some particular size, and the cost would be how long it takes for you to read a page or write a page on disk. Okay. And the cost of database operation, like when you want to insert something, delete something, query for something, um, we will measure by the page IOs. Okay, so we will not care much about CPU time, as I mentioned, because comparing with the page IO really dominates. Okay. And our main goal is to try to minimize the page IO as much as we could. Okay. And then we see through indexing, we can actually achieve that goal. Okay, so that's a typical things that you could see at some facility that like hosts a database server, or like, yeah, even here at Jula, if you go for Rectula clusters or whatever, you probably see something like that, but not like the whole room, but we have racks and racks of servers for different type of servers, including the database servers as well. Okay. And what do we have for those servers? Mostly disk. Okay. And we have different types of disks these days. We have, in the old days, we have tapes. Like, um, yeah, probably you have seen some tapes before, right? With the winding, like tape stuff. Okay. For tapes, it's a sequential access device. So you cannot just jump to a particular part of the tape like right away. You have to like fast forward and rewind the tape, just like the correction tape that you use, the whiteout thing. You can't just skip. You have to go sequentially, right? So imagine if you store things on tape. When you want to access something, you have to like wait until the head goes to a particular part of the tape, right? So everything goes sequentially. It's cheaper than disk. Most of the time, we use it for archival storage because it's just too slow these days comparing to our expectation. So we moved on to this a long time ago. We have hard disk, like hard disk, spinning disk. You probably, yeah, you're in the era that, yeah, you have seen the disk there, and you have solid state drive these days without the spinning disk anymore. But all of those disks, they are random access device. That means you can actually skip to particular part of the disk like randomly. You don't have to read consecutive page or consecutive, you don't have to go sequentially, right? But let's say in the spinning disk, of course, if you read consecutive page, it will be cheaper than reading random part of the page, right? Of course, because we have some proximity. Like if it's closer together in the blocks, it's going to be a little faster. Okay. And do we still have tapes these days? Yes. And do we still use tapes? Yes. And what about archival storage? We still use tape? Yes. Okay. And you probably ask, okay, why do we still need tape? Because the disk is much cheaper these days. And we have terabyte size tapes. We can archive things there. But the thing is, the tape is more durable. Okay. We talk about 25, 30 years of storage without any much of a problem. But if we go for solid state drive, like you say, oh, it's very fast and it's not that expensive. I have all the money to spend on archival using the solid state drive. But that's not good because you have to understand the technology that solid state drive needs some electricity for it to hold the information. So you need some batteries or something there. So if you store it for, let's say, a few years, it's dead. So the information will be, well, it dies. The hard drive, it's a little better in terms of how long it could hold the thing, but it's magnetic drive. So it could flip the bits too. Yeah, in a sense, but it could stay longer than solid state drive. So in terms of archival, part. If you don't like tapes, you can go with magnetic disc. Okay, that's spinning disk drive, hard drive. Okay, but for most companies, they still use tapes for archival. So these are the tapes. And in these days, we can have robots to like take different parts of the tape out when you want to search for things, right? Okay. And when we talk about relations or tables, let's say we create a table, we stored um, some records. How are they stored on disk? Well, a relation or a table. Each record has a record ID, or in short, we call it RID, record ID. We use it to locate the record. In OS, well, we have page ID, page number, things like that. So it's something very similar. That's a pointer that points to the particular part of the physical disk. Okay. And this is handled by OS in the file system part. Okay. And all of these things, we have a structure so that we could support all the file operation. Like we can do a query, we can do insertion, deletion, do sequential scan, things like that. Okay. And as an OS, they need to keep track of empty pages so that when we want to insert something new into the database, we have to know which page is empty enough for you to insert a new data in. So that's part of the OS that needs to take care of those stuff. Okay. Now, anybody could guess what this is for? Have you ever seen it, or could you guess? Mailboxes? Not really. Okay, it's about this size for each. Okay, now let's see a little hint, more hint. There, it's little like drawer. Yeah. And it has some cards inside. How many of you have seen something similar to this? Well, you're too young now, like you're baby. This is gone from your life. Well, actually, if you visit some of the libraries, they probably could have some as a historical thing there for you to look at. Um, I went to our library here. They don't have it anymore, but they have it like a small set in a little separated room. Just just the sake of having it in case someone wants to see. Okay. Now let's take a look at what these cards are. Okay. In the card, actually, this is called index card. Okay. So in the old days, you probably have seen in the stationery section, they sell something called index card. So that's this side of the card. And they called index card for a reason because yes, they use those cards in all these the cabinet things. Okay, in the card, we will put information. Well, this is the index card for the library. Okay, we can have index card for different type of things as well. But for the library, let's say we have 10,000 books in the library. We would need to have 10,000 cards. And each card will contain the information about that particular book, one particular book. So here we have an author part. We have the title of the book. We have some other things like number of pages, physical description, the height or whatever, and also the call number. Like, so you would know where we could get to the shelf. Okay. So these days, instead of having this, we will have a terminal computer, right? When you go to the library, here or Hall Klang, whatever, you have a computer, and then it will ask you what you want to search for. You want to search based on that the author, the title, the keywords, whatever. But you would have this numbers as well, so that it would direct you to which part of the library you can access that particular book. Okay, it will probably see which level of the library and which shelf and things like that. So this is the same thing, but this is predated computer. Okay. And when we put all 10,000 cards together, we need to sort them somehow so that we can search for it very quickly. Because out of 10,000 books, if you have to go through all the like random stuff, it will be not fun, right? So if we need to sort this card, what should we sort based on? The title, the author, what? Right? If one card represents one book. So depending on, you have to think about when people wants to search for the book, what do they search on? Let's say if they search on the title book. So you have to imagine, okay, we have 10,000 cards representing 10,000 books. We have to sort these 10,000 cards based on title. Okay, so when we want to search for title, we can get to that particular card faster, right? But well, some people comes in and didn't really want to search based on title. They want to search on author. So what do? We can use the same set of cards, but now we're lost because it's sorted based on title, not the author. But can we get to the answer? Yes, we can go through all of them. And eventually, at the end of the day, you say, okay, I found it. Or maybe you go through all of them and it's not there because the book is not in the library, right? But yeah, you can get to the answer, but not fast. To make it fast, you have to add another 10,000 cards and copy exactly the same thing as before, another 10,000. But now we sort based on authors. So you have another set of 10,000 cards, sort on author. And then let's say if somebody comes in and want to search based on keywords, oh no, the two sets are not enough anymore. We have to buy 10,000 more cards. And then having the same exactly information, but sort differently. Okay, this is called indexing. Okay, even now with the computer, when you go to the computer in the library, it will have the links for you. Oh, you want to search based on what? Based on author. You click on the author and then you search. You click on title, you sort based on title, and then search based on ISBN, or you can click on ISBN and so on, right? But you have to understand that every time you clicked on it, well, that's another structure that you have to build and to sort based on that search key. Okay, that would be the overhead that you have to pay for having something have some structure that you can search faster. Okay, otherwise, well, with 10,000 books, good luck. You go find them. Okay, so having index structure, it's not going to have you have different result, or like if the book is there, you will eventually find it. But if it's not there, you will know that it's not there. But the difference is how fast you could find that out. Okay. Having index would not change the result. The only thing that matters is the time it takes. That's all. So indexing is for speeding up the search. That's it. Okay. You should get exactly the same thing as before, but faster. Okay. That's the whole idea of indexing. All right. Okay. Now, before we get into the indexing part, we will look at different types of file organization that we could see these days. We have something called heap, which is not the same heap as you did in data structure. Remember, you had something called heap, and then you have to heapify. No, different thing. Okay, this is a heap file, which is the very primitive type of file, which is the random order. Let's say we add something in, we just keep putting in, append it to the end, and we don't care about the order. That's a random order file. We call it heap files. Okay. Another organization is called sorted file. So if we have heap and it's not in sorted order, and sometimes you want to search something faster, so okay, let's maintain the sorted order. So we sort them and keep them sorted at all time. When you want to insert something, we have to make sure they insert in a sorted way so that when you want to search for things, we can do it faster. That's a sorted file. And then another organization is called index. Okay. The sorted files is just a raw file, but you just put in different order, make sure that it's in some order that you want based on some search keys. Okay. But index is another structure. It's not part of the raw data because you already have raw data somehow. Index is something extra that you created. So that's an overhead that you created, but it's a structure that could organize the record somehow so that when you want to search for things, you can do it faster. Okay, that's index. Now the reason why I put indexes slash indices is well, well the original word is index, right? The plural form is what? Indices, right? Indices. The correct one is indices. But you could probably see the word indexes in several textbooks these days, but it's not the valid English word, though. The correct one is indices. But these days, well, it's more like terminology that, okay, I accept indexes as the plural of index. Okay. So just to let you know that you probably see the variation there. Okay. So we will look at how index is done in this lecture and the next lecture. And it's somehow similar to sorted files, but we have extra data structure so that things can be done quickly, both in terms of updates, like every time we insert, we delete something, we have some overheads, something like that. But index is trying to like compromise everything and makes overall performance faster than the sorted file. But we'll look at the cost analysis in the next lecture that you will be able to compare how much it costs for different types of operations. Okay, let's take a look at this intuition. Let's say I have 22 data records from number 1 to number 22, and I have last names of people in random order. Okay. So let's say if I want to search for some particular last name, let's say I want to find someone called Winter. What's the search time that I will need if everything is in random order like this? What's the best case? What's the maximum search time? What's the average search time? But since you have, well, taken like all the data structure class and everything, you should be able to, an algorithm, right? So you should be able to like guess, not guess, you have to know it, right? Okay, what's the best case? You can find it instantly in the first row, and that's your answer. That's a best case, right? What's the worst case? You had to go through, and that's 22, like row 22 that you see your answer. And what's the average case? Somewhere in the middle, right? Or if you want to be exact, well, from the best case, you have 1 plus 2 plus 3 plus 4 plus until n divided by n, right? So n times n plus 1 over 2 divided by n. So that's, yeah. So what is it? N plus 1 over 2, right? That's the average case. So roughly in the middle, that's the average case, right? Can we do better? Of course. So let's say if something changes a little bit, I reordered the rows so that it's sorted based on last name in alphabetical order. What's the base case in this case? Still like 1, right? Instant. What's the maximum search time? Or depending on what scheme you use to search for things. If you still do it sequentially, well, that's the same thing as before, right? But if you want to use the fact that it's sorted, you could do something better, right? You can, what can you do? Binary search. Yes, yes, yes. Binary search, binary search. Very simple binary search can get this thing done in log time, right? Base 2, log base 2, log of n base 2. What about the average case? So that's the worst case. What about the average case? The same thing, right? The same thing as worst case, roughly. Yes. So comparing between this case and the randomly ordered case, you'll see that if you put things in sorted order, you can search for things faster, right? Even on average case, right? And the worst case is the same as average case. So that's pretty good. So somehow we need to be able to sort things so that we could access things faster later. Okay, now back to index. Okay. Like I mentioned, indexing is the mechanism to speed up access to the data we want so that all the operations is done faster, like both in terms of insertion, deletion, scanning, like any queries would be faster. Okay. And also in your project, you will have to at least implement some of the indexing scheme as well, like at least one there just to make sure that you know how to do it. And you probably could see the difference if it could actually speed up things for your project. Okay, now we have some terminologies. We have something called search key. Search key are things that you want to search based on, just like in the library case. We have search key that is called title. So if you want to search things based on title, title will use search key. If you want to search based on the author, author would be your search key. If you want to search based on ISBN, ISBN would be your search key. Okay. So search key is some attribute that you want to be able to search faster based on. Okay. And the search key can just be one particular, one single attribute, or it could be composite attributes, like multiple attributes together. That could be done as well. And just to emphasize, search key is not the same as key that we did before a midterm, right? Those keys are like candidate key, primary key, and those type of keys. That's a different thing. Okay, search key is for index. Okay, the basic concept of the index file, it contains something called data entries. And this could confuse a lot of you because it says data entry, but it's not actually the data. Okay, when you hear something called data entry, you have to think that's index entry, not the data, data. If it's the data, we call it data file. Okay, if it's data entry, sometimes we call it index entry, but in some textbook, they call it data entries just to confuse you for some reason. Okay, and the index file would contain something very minimal, which are the search key and the pointer. Let's say your data record could contain 20 attributes, but the search key could just contain only things that you want to search on. So you can just pick the search key that we want, and then we create the index file based on just those. The search key and the pointer that points to the physical record. Okay. And since we only pick the search key that we want, so the index file usually would be smaller size than original files. Because original files, you could have like 20, 50 fields, but you only pick only one field out of those for search key or 2, 3 fields out of those. So usually it will be much smaller. And we have two basic types of indices, which things that we will cover today, which are the order indices, which is tree-based index, and the hash indices that's based on like hash function and buckets. Okay, now let's take a look at a simple data entry. Let's say we have very, very simple data records. This is my raw data containing only 3 fields. We have the name, we have age and salary. And right now the data record is sorted by name. So alphabetically. So B, C, I, and S there. And if you want to search based on name, we can do it fast because since it's sorted based on name right here, we can use binary search to look for the particular record fast. But if you want to search based on salary or age, if you only have this table, you cannot do that very fast because it's not sorted on age, it's not sorted on salary. So what you could do is you can create an additional index structure. So here, if we know that in the future we may want to search based on age, we just create another structure. This is a search key, which is age, followed by the pointer. So that's another field, pointer that points to the physical record. And now it's sorted based on age. So if you want to look for things based on age, you can use binary search on this index file in data entries. We can look for things faster now. But if you want to search based on salary and we don't have anything sorted on salary just yet, we can create another set of data entries. And we just pick only the salary part and we sort based on those. And then we have pointer that points to the actual data record. So now, if you want to search based on name, you can do it fast. If you want to search based on age and salary, you can do it fast because we have all the search keys sorted in that order. Okay. Okay. So the search key does not have to correspond one by one with the data record. We can have one search key and pointer that could correspond to block of things there. Yeah. You could save some pointers if you want to, or they have different schemes that could actually well, we call it sparse index and dense index. If it's dense, that means every search key will have to correspond to like every single data records will have corresponding index structure for it. But if it's like this, it's called sparse index because not all of them have the index for. But this search key can well take care of all these blocks. This one will take care of all these blocks and so on. Okay. Before we go on, for data entries or index, we have three alternatives of the structure that you have to really understand. Otherwise, when we look at the cost analysis, you won't be able to do it. Okay. The first one, alternative one, the data entry is an actual data record, Okay. So if you look back here, this is called alternative one. Okay. This is alternative one. Why? Because it is a raw data. And when you want to sort on things, we sort on the whole data record, like all the fields together as a whole. So since we have only one set of data records, we can only have one set of alternative one, right? If you want to sort based on something else, you have to do like data entries, like the age and the salary. That. Okay, so alternative one, we will have a little notion with the little star there, just to let you know that, oh, okay, this is the raw data. It's not the extra index structure that you created. Okay, so it's actual data. So when you want to delete something with the star, you have to really think, oh, do we really need to delete that data out of your database or not? But if it's part of the index structure, that doesn't really matter because index is the things that is add on to your raw data. Okay. The next one is alternative two. We have the data entry that contains search key and the RID or the pointer. So that's very similar to the one that we saw earlier, like the age and the salary. We only pick the search key that we want, the age alone or salary alone, and each one will have the record ID or the pointer that points to the actual data record. Okay, so that's called alternative 2. So since we only have one possible alternative 1 for a table, the rest has to be alternative 2 or 3. Now, 2 and 3 are very similar, except that for alternative 3, instead of having one single RID for each one, we can group RID that are the same together with the same the same search key. If they have the same search key, we can put them into RID list in the same item. Okay, the advantage of alternative 2 and 3, well, of course, it's smaller, and we can do it unlimitedly because we can create each alternative 2 or 3 for each one of the search key that we want. Alternative 3 is better than 2 because it has a better space utilization because we group RID into the list. Okay, we see that in just a little bit. Okay, now this is a part of the textbook. This is the index part, the back of the book. Can you guess from the keywords there, which textbook is this? It's the textbook that you use for your past courses. We have sorting, we have statements, we have, yeah. Can you guess? Well, actually, this is from discrete math textbook. Yeah. Okay, now, what do you think, which alternative this is? 1 or 2 or 3? Is it 1? Not 1, because if it's 1, it's a whole textbook, right? All the content, which is not there. Now, alternative 2 or 3, then. If you look here, you can see that if we want topological sort, that's a list, right? You can go to 627 to 629 and also 634. That's alternative 3, right? Because we have the list of record ID or the pointers that point to different pages, right? If it is alternative 2, what will that look like? If it's 2, let's say if you have bubble sort, you have bubble 196, bubble 232, like in different lines. So, well, this case, you would save some space of repeating the same search key. Okay, so this is alternative 3. What about this one? This is also a type of index. This is table of content from the same textbook. Is this alternative 1 or 2 or 3? Not 1 because it's not the content. 2, 3, 2, right? Alternative 2, right? Okay, good. And actually, the difference between the table of content and the index part in the back of the book are the order of the index. If it's table of content, you see that the page number is in increasing order, right? Or non-decreasing order, I have to say, right? So it has similar order as the content, the actual raw data, right? So you see you see number theory first, and then you see counting later, something like that, following all these ordering. But if you look at the index at the back of the textbook, if you look at the page number, it's not in the same order of how the content is ordered, right? So that's a different ordering. And this would actually matters when it comes to the cost analysis that we have to look at next time. All right. All right. Now for today, we are going to look really quickly on two things, tree-based indexing and hash-based indexing. In the old curriculum, actually, we will took a lot of time on this thing. We have one whole lecture on tree-based indexing, one whole lecture on hash-based. But yeah, well, we're going to put everything together in one lecture. So yeah, to wrap things up for you. First, let's look at tree structure indexing. First, we look at something called ISAM. So if you started implementing your project in a database, and if you explore indexing, you will see ISAM as one of the options to do the index. Okay. And well, as it says, well, we understand what ISAM is, and then we see why it's not good. So we have to do something else called B plus tree. And in the DBMS, we will see something called B tree in there. So you have to know the difference between the two so that you could pick them accordingly that fits your need the most. Okay, now let's take a look at ISAM first. ISAM stands for Index Sequential Access Method, right? It's a tree base, right? And it's very similar to something called sorted files that we talked about earlier. So things are stored on pages, like in data pages, whatever, and everything is sorted. And you can imagine that if we want to search for things when something is sorted, well, we can do it fast, relatively faster using binary search tree or whatever structure on top. All right. So with the binary search, we can do things faster. Instead of big O of n, we can do big O of log n, of course. Okay, so it seems like we're doing fine, right, with ISAM. We can search for things in log time, right? And well, why is it fast? Because we use the binary search tree. And if you look at the index entry would contain the key and the pointer pair, right? Depending on what the search key would be, let's say the search key is on name. Um, well, anything that is to the right of the search key would be greater than or equals to that search key value. And things to the left would be something less than that particular value of the search key. Okay, so we can use index entry to navigate or to direct the search into data page that we want. And actually, it can point to only one data page. And then the rest you can just ignore because we know that since it's sorted, so we know that it's not going to be in that particular data page. And that would make things faster because we can ignore a lot of stuff. Okay. And if it is a binary search, back to the binary search, we have one search key in one node, and then we have two pointers left and right, right? But in index sequential access method in ISAM, we can have bigger node. We can have more than one search key. So we can have, let's say the node of size 50, size 100 or whatever. And then we have the pointers that points to different nodes as well. So why would this be better than binary search? Because for binary search, we only have left and right, only two pointers per node. But if you have 10 pointers per node, 50 pointers per node, we can actually have a shorter height of the tree. So we can access things, we can get to the leaf node really fast because we can only need probably 2 or 3 access. We see later how much improvement we can achieve with the size of the node, like 50, 100, and more. Okay, so here in the typical binary search tree, we have one slots for the search key, and then we have pointers left and right. Anything to the left of that search key would be less than 7. Anything to the right would be 7 or more. Very simple. And we could have bigger node, as I mentioned. And here, everything must follow the same the same rules. So here, data page 1 would be everything less than 5, and data page 2 would be 5 or more but less than 12, and so on. So here, data page n-1 would be 16 or more but less than 19. Data page n would be 19 or more, so on. So everything must be sorted, both in terms of data pages, data there, and also the index file must also be sorted. So it's easy, 5, 12, 16, 19, everything is sorted. Okay, if you want to search for number 8, well, easy way, you go to the root node and then look for um, which subtree we would have to go. So here 8 would be between 5 and 12, so you go to data page 2, and then well, we just look for things there. If it's there, it's there. If it's not there, you can say that it's not in the database. We don't have to go look in data page 1, 3, 4, 5, 6, 7. We don't need to do that because everything is already sorted. If it's there, it must be there. All right. And another point would be, how big should the index file be? Can we make this really detailed in a smaller resolution so that we have more than one pointer that point to one page? So instead of in the previous one, so one pointer points to the beginning of data page. But this variation, we have something points to the middle of the page. Would that help if we have more pointers per page? Well, not really. Even though we can say that, oh, we can get to the middle of the blocks, but we have to retrieve the whole block each time anyway. So doesn't really help much. Okay, so just to make it simple, we just put one pointer per page. That would be good enough. But can we have less? In this case, instead of having more than one pointer per page, now we have more pages per one pointer. So here we have one pointer per 2 pages. Would that be good? We have less pointers per page. Well, the things that it will affect is the index file size. It will be smaller because we need less pointers to point to all the pages. But when we search for things, if something is in page 2, we have to start following and go to data page 1 first, and then follow the link to data page 2. So it would be a little slower comparing to one pointer per page. But well, of course, the index file size would be smaller. All right. But let's say we have index file, but somehow index file size is big, so big that it does not fit in main memory. So we could break index file into small chunks, and then we have index of index. So we would form something like called a tree structure, like index of index, which is fine, right? And this is what we will have usually on our database. So index of index is just a tree. So we have, let's say we have this tree, like ISAM tree there. You see that everything is still sorted, right? Sorted. So 5, 13, 14, 16, 17, 18, 30, 35, 43, everything is sorted. And also everything in data pages must also be sorted. Okay, now how would this make things faster for the search? If you want to search for 15, find 15, you start from the root node and you follow the left subtree, less than 17 there. And then 15 must be data page 4. And then we look for things in data page 4. If it's there, you would see it. If it's not there, you would say that, it's not in your database. Okay, if you want to find 0, that's the same thing. Find 0, you follow there, go to data page 1, and then you get to see your 0. What about range search? Range search, you could, let's say if I want to find something 15 or more. So we start with finding 15. So 15 would be in data page 4, and then we can scoop everything there because actually all of them would have sideway pointers back and forth so that when we see number 15, we can gather the rest of the items until the rest of the data page. So that's range search could be done really efficiently with the tree-based structure because everything is already sorted. Very handy. Okay. Now it seems like our ISAM is very nice and good enough, right? So what's the problem? The problem occurs when we have deletion and insertion. And now let's see what type of problem we have there. If we delete, if we keep deleting stuff from out of, say, data page 2, so the worst case would be empty page and nothing there. So it's like a waste of storage. So that's not a big of a problem. It's just the waste of storage. But if we have insertion, that would be more a bigger problem. Let's say if we insert something 15 in the data page. So let's say 15 must be in data page 4, and then we keep inserting stuff in there, and then it's full. And then we keep inserting another item there. It is full, so what do? Can we spill over to data page 5 or spill over to data page 3? No, we cannot do that because according to the index, the search key there, 15 must be here, right? So the only way that we could do is we add the overflow page. So that's the overflow from page 2. So things can spill over and stay in overflow page. Well, it seems okay, but let's say if you keep inserting something in data page 4 again and again until overflow page 1 is full. So we need another overflow page, keep on adding. So at the end, we could have long overflow chain. And when we want to search for things in data page 4, what do we have to do? We have to search from the first page of data page 4 through the whole overflow chain. That could take a bit longer time. So we see, okay, if we could avoid all the overflow pages altogether, would that be better? Yes, of course, because we don't have to go through the long chain of pages. Okay, that's when B plus 3 comes in. Okay, B plus 3 makes sure that there's never, ever going to be overflow pages. But it comes with a price because we need to make sure that we have to adjust the tree somehow so that the overflow would never, ever develop. Okay. So B plus tree index is the, I have to call it the dynamic structure. For ISAM, it is static structure. That means that we may start off with 10 data pages. And then when we keep adding things, we will end up with overflow. So if you want to adjust something, you have to reorganize the whole thing. Okay, make sure that we break out all the overflows, and then we have maybe 15 pages now. You have to reorganize the whole thing over and over. So that's called static structure. But for B plus tree, it is dynamic. Every time it needs some more pages, it will adjust right away, locally or globally, whatever, but adjust right then and there when we need a new page. Okay. But when it is dynamic, that means that you have overhead of doing the adjustment every time you do insertion or deletion. Okay, this is the B plus tree index structure. It looks very much similar to ISAM, right? Very similar. We have the root node, we have non-leaf nodes, we have leaf nodes. Okay. All the leaf nodes, depending on which alternative you have. If it's alternative 1, all the data records will be inside the leaf page. But if it's alternative 2 or 3, we will have leaf page, and then we have something pointers point to the actual data record again. Okay. So if you look at the structure itself, it looks very similar to ISAM. But the main difference, well, what's the difference? The root nodes are the same. We have root node. The non-leaf nodes, well, we also have something very similar structure. We have search keys, and then we have pointers. Okay. What are the difference? leaf page contain data entries and are chained. Well, that's the same. So here, that's the difference. This is the difference between B plus tree and ISAM. The length of the path from root node to leaf node must be the same for the whole tree. So if there is a path from root node to leaf node, they must have the same height all over. Okay, you cannot have height 2 on this path, height 3 on this path, and so on. No, you cannot do that. In B plus tree, you must have exactly the same height on all the path available. Okay, so the same height, balance in height. And well, the number of pointers per node for binary tree, that's 2, right? We call it fan out. That's a terminology that we use. A fan out is the available pointers per node. Okay. For both ISAM and B plus tree, we have a larger fan out, okay, comparing with the binary tree. Okay. Now, what's the bad thing for ISAM? Why do we have to move away from ISAM sometimes? It's when the file grows. So if you have pretty much like complete database with not a lot of insertion, ISAM is good enough. Actually, better than B plus tree because it's faster because it doesn't have a lot of overheads. But if we have a lot of insertion going on, a lot of deletion, a lot of insertion, so it's very dynamic database. So B plus tree is much better than ISAM because it adjusts the tree itself so that it has balanced height tree at all time, so that the time it takes to get from the root node to leaf node it's fast on all the paths. Okay, so when we need to have, if you have to maintain dynamic database, ISAM is not good. Okay. For B plus tree, it automatically reorganizes itself with some local changes, mostly local changes. In a rare case, the way we have to propagate the changes and have the height chain and things like that we will see a little later. And we have to make sure that we have to maintain the index structure. Every time we insert, every time we delete, we have to look at all the property and make sure it has the B plus tree property at all time. So that's the overheads that we have to accept. But for dynamic database, we say that B plus tree has advantage that outweigh its advantages, and we still use them these days. And we could see in your DBMS that both ISAM and B3 are used. Well, it depends on your usage. If it's non-dynamic database, ISAM is better. All right. Okay. Now, again, on properties of B plus tree. All paths from root to leaf nodes are the same length. And then we have something called order of the tree. Sometimes we call it fill factor. Sometimes we call it load factor. This is the, some parameter that tells you how much we need to maintain something in a node. Like in this case, if we make it simple, we say the order of the tree is n/2, which is half. We have to make sure that the node is half full at all time. Half full means that if you have 4 slots for the search key, 4 slots, if you have 4 slots for search key, that means we have 5 pointer slots, right? 1, 2, 3, 4, 5. Half full, that means out of 4 slots for search key, we need to use 2 out of 4 at least at all time. And out of 5 pointers, we need to use at least 3 out of 5 because 2 out of 5 is not half yet, right? So at least 3 out of 5 pointers must be used for each node. So that's the order of the tree. We can adjust this to like 3/4, 1/2, 1/4, whatever, depending on how much you expect to see new insertion. Because if we leave the space a lot, that means it has more space for the future insertion without having to split 4 more nodes. Okay. But actually, all these things, usually the DBMS will determine it for you. Okay. And all these things, n over 2, the ceiling, n minus 1 over 2, and all, these are the things that determine, like, it's a half full number. Okay. And we have a little special case that the root node does not have to follow all these property. At least if it has 2 children or 2 pointers out of the whole node for root node is used, it's good enough. Okay. So the B plus 3 node structure, like I said, very similar to ISAM. We have different K for storage key values, also must be sorted. And then P, all the P's are the pointers that points to a different subtree. Okay. Okay, here, that's the node of size 3, n equals to 3, n is number of available pointers. Okay. So n minus 1 over 2 and n minus 1. Well, for n equals to 3, that means we the leaf node must have between 1 and 2 values. So this is to determine how much items you need to use as slots for the search key. So out of 2 slots, we need to have at least 1 slot occupied, half full. Non-leaf nodes, that's determine how many pointers that we need to use per node. So for n equals to 3, at least 2 out of 3 must be used. And then the root node must have at least 2 children. So you could see that all the paths have the same height. 1, 2, 1, 2, 1, 2, 1, 2. They all have the same height. We do not care about the path that is not there. Okay. You said, oh, there's no path, that's 0. No, we only count if there is available path from root to leaf nodes. And if there is such the path, the height must be the same for the whole tree. So this is a valid B plus tree. This is another valid B plus tree, except that this one is not called a non-leaf node. It's called a root node. So it follows an exception that if 2 out of whatever is used, it's good enough for the root node. And here we have n equals to 5. So at least for 4 slots here, 2 out of 4 must be used. And for the pointers, if we have non-leaf nodes in between, at least 3 out of 5 pointers must be used. Okay, the queries on B plus tree is the same as ISAM because it has very similar tree structure. We start off from the root node and then we traverse the tree based on the search key value. Okay, so that's the same thing for searching for things. Okay, now the good thing about having ISAM or B plus tree with large size nodes. Here with the fan out equals to 100. So instead of having fan out 2, like binary tree, we have fan out 100. We can actually accommodate 100 million items with just height of 4. Very nice. Log base 100 of 100 million. That's only 4 nodes access. If you compare that with binary tree, well, that's log base 2 of 100 million. That's about 26 nodes. So the height of 26 versus height of 4. Well, that's a big difference. If you have to, for each node, you have to access a disk for that. So that's a big improvement in terms of the I/O. Okay. And you may ask, what's the typical values for fan out in DBMS? It varies, but depending on how large your search key would be or how large your data records would be. But typically it's 100 to 400. To think about if you have a node size of 400, well, the height of the tree is really small. Like 1 or 2, you get to your leaf node already. Okay. Okay. Now let's take a look at some examples. That's a queries on B plus tree, which is the same as the ISAM queries. So here, if you want to find 28, you start from the root node. 28 goes to the right subtree and 28 is here. So if you get there, you see 27, you see 29, and then you know that you could stop. 28 is not in my database. I don't have to look at any other pages because everything is sorted. So it's done. If you want to find number 0, you start from the root node, you go to left subtree and go left subtree again. So once you see number 2, you can stop right away because there is no point of going further because 0 is not there. If you want to find all records greater than 25, you start from the root node again and look for 25 to start off with. 25, you go to that node, and then you look for something greater than 25. So you know that it must be on the next node. So we have the side wheel pointers that points to the next node, and then you can scoop the rest of the items as the answer. So you get 27, 29, 33, 34, 38, 39 as the answer for the result of the queries. Okay, now the important part comes because this is the main difference between ISAM and B plus tree. It's when the insertion comes. For ISAM, we have overflow page just attached to the original page. But here, if we have overflow page, the height from root to leaf node will be different. It will not have height balance anymore. So we have to break that off, make sure that everything is height balanced. Okay, so what are we going to do with insertion? So usually we need to find out where exactly we should insert the stuff in. If there is a space there, we put it in and then we're done. This is the easiest case of all. There's nothing changes. That's the same thing as ISAM. But the things come when the node is full. Instead of adding the overflow page, we do something. Well, if there is a room, we put it in there. But if there is no room there, we have to split the node. Okay, this is important step. We have to split the nodes so that instead of having one node, we have two nodes now. But two nodes, it must be on the same level. We would not put in like different levels like ISAM as an overflow. We split in the side way in the same direction there. But the problem is we may not have we may not have enough pointers to point to extra node. So we have to do some adjustment accordingly. Okay, now let's take a look at the example here. If you want to insert number 23 in your database, so start off with the root node. 23 is there. And then we have room there. So we put 23 there and we're done. This is the easiest case of all for B plus tree. So the same as ISAM as well. Easy. Okay, now with the more challenging thing. If we want to insert 8, okay, insert 8 in there. So we start from the root node. 8 is, well, this subtree, right? 8. So we know that we have to insert into the first page. Okay, look carefully. The node is full. We have 2, 3, 5, 7 is already full. What we need to do is we need to do the node splitting. The rest of the nodes look exactly the same. So all of these things stay exactly the same. Nothing changes. What we have to do is you split the node into 2. And instead of having 4 slots, now we have 8 slots total. We are going to split 5 items into 8 slots, right? Because originally we have 4 items. We have one more item, number 8 there. So we have 5 items in 8 slots. So how do we spread the items? So we have 2 ways to do. Given that, assuming we have a fill factor of like order of the tree is half full. So we have to make sure that at least 2 out of 4 slots must be used. Okay. So there are 2 schemes. The first one is spreading 2 and 3, or another one 3 and 2. That's it. That's the 2 ways. If you split 2 and 3, 2 items first, so 2, 3 in one node, the other one is 5, 7, and 8. Well, that's fine. Or you could do this. You could have 2, 3, 5. And then 7 and 8 there. Well, that's another way. So we can do it either way. But if you pick 2, 3, and 5, 7, 8 there, the next step would be since we have two nodes, but here we only have one space for the pointer, we have only one available pointer, so we cannot have one pointer points to both nodes, right? So what we have to do is we have to create an index for these two nodes, the index for these two nodes. So what's a search key that would be good to hold this two nodes? Well, here I put number 5 there. That means the left subtree of the 5 would be something less than 5. Anything to the right would be 5 or more, which is good. Okay, it's okay. But the question is, does it have to be 5? Can it have 4 there? Will 4 be okay? Yes, right? Because less than 4, well, 2 and 3 is less than 4. 5, 7, 8 would be more than 4. Can it be 4.5? Yes. It can be 4.5. Can it be 4.99? Yes, it could. Can it be 5.1? No, it cannot be 5.1, right? Because it has to be 5 or more. So the thing is, the number here you can have, well, a lot of choices, right? But if you have to keep determining what number should I put there, well, we don't have to determine that all the time. The easiest way to do is you just pick the smallest value there, and then we use that as well, as the index value, right? Because it will always hold for that property, right? Okay, so that's easy. So we just pick the smallest values there and then use that. But if you use this one, the index value would have to be 7, right? Otherwise, it would not, the number 5 cannot stay there. All right. Okay, next step is that if we have 5 as a search key for these two nodes, okay, so that's one node. Can I just connect this to there? No. Well, it seems okay, but if you connect it, the height from root to leaf would not be height balance anymore for the whole tree, right? That's not cool. We don't want that to happen. So what do we do? What we have to do is we are going to insert this thing into the parent node. Insert into the parent node. But parent node is obviously full. So we do the same thing again. Whenever the node is full, we split the node into 2. So here we insert this in there, and 13, 17, 24, 30, it's full. So we split into 2 nodes. Now we have 5, 13, 17, 24, 30. And then we spread the values across. But now the difference between the two, before we copied the value 5. Well, if you look here, the 5 got copied up because we cannot push number 5 away because 5 is part of the raw data with the star there. It's a data, the actual data. So 5 that we created, that's the extra value that we created as the index structure. But in the non-leaf nodes, it's different. We have 5, 13, 17, 24, 30. We can actually, well, before you may think, okay, we have 5 and 13, and then we have 17, 24, 30, and then we have 17 up there. Would that be okay? Well, actually, this is different from the previous ones because the one that we did with 5 is with the leaf node. The leaf node is done without any extra pointers. There is no more pointers pointing away from the leaf node, right? But this one is different. We have pointers there. So the value there, 17, got pushed up, not copied up. Um, it's it's nothing deep there, but we just try to optimize the usage of the pointer. So if you look here, if you copy 17 up, you know that in this subtree, it will be greater than equals to 17. But here, it will be less than 17. So we know that this thing would never have anything get to that, right? It's a wasteful pointer, right? We only need this one that goes from 17 to 24, right? So if we push 17 up, we will not waste any pointer because this one would be greater than or equals to 17, and this one would be 17 or more, but less than 24 as we wanted. Okay, and at the end, we just connect everything together, and we have a nice B plus tree with that same height balance in the whole tree. So with all the available paths from root node to leaf node, we have the same height balance. And this is the rare case that after one insertion, we have the height increase. The maximum height increase for B plus tree is only one. It's already rare because you could see that 100 million search keys, we only need height of 4. So to increase the height by 1, that means you need to have a lot of full nodes, right? Okay, so in this case, insertion of 8 has split the node and then increased the height of B plus tree by 1. Okay, so this is all the explanation of what we just did for splitting the node. All right. All right, here's another example with well, alphabetical words there. If you want to insert clear view into the tree, start off from the root node. Clear view is in this subtree. So we need to add clear view into the node, but the node is full, right? Node is full. So we need to split the node. So we split the node, we have Brighton, downtown, and Clearview. So we have 4 slots for 3 items. So you could spread them Brighton, Clearview in one node and downtown in another node. Or you can have Brighton alone in one node and Clearview downtown in another node. That's also possible. Okay, now we split the node and then we have this. So we pick downtown as the search key and then we insert into the parent node. So insert downtown into the parent node there. Make sure that everything is sorted in sorted order. So we have to push minus away to the right and make sure that downtown comes before minus, right? Okay, and the rest, since we have available pointers there, so everything has the pointer that points to its own node, and then we're done. So in this case, you could see that even though there is a node splitting, it doesn't mean that we need to increase the height all the time. Because most of the time it will fall into this category that we split a node, but we have some other way, like other space in other level, so that we don't need to actually increase the height. Okay, now in reverse, if you want to delete something in ISAM, usually deletion doesn't really cause that much of a problem. It's just the waste space for the node. But deletion in B plus tree actually cause you problems if the node is too lonely. It's less filled up, not up to the order of the tree. So we need to merge the node back, right? So let's say we have 4 slots and then we have 2 out of 4, and then we delete 1 away. We have 1 left. So that's too lonely. We have to do something. We have to merge the node back. Okay. And the deletion, sometimes if we keep merging the nodes, the worst case would be height decrease because we merge until we don't need the root node anymore. So the height got decreased by 1. So the worst case for the insertion is height increased by 1. And for deletion, we could decrease the height by 1 as well. We never ever have node increase or decrease by more than 1 for B plus tree. Okay, so here's example. We have three variation of deletion in B plus tree. In here, we want to delete downtown. So we want to delete this one away. So if downtown is gone, that means the search key downtown here must be gone as well. So when this one is gone, we don't need this node. This node is gone. So we adjust back to this, and then we're done. This is for deletion. And here we have height decrease. We want to delete per reach out of the database. For per reach is here. So we delete this one away. So when we delete this one, this pointer has to be gone as well. So when this pointer is gone, this node is too empty because we have 3 slots for the pointer, but only one pointer is used. So it's too lonely. So we need to merge these things together, merge 2 nodes together. So minus and redwood comes together. So we don't need this one anymore. And in this case, the height got decreased by 1. And then in the last case, we delete per reach again here. We delete per reach there. And so this one is gone. This one is too lonely, but we cannot merge the node because the merge to the left is already full. So what we could do is we can borrow pointer from the siblings. Well, we can readjust them to make sure that we have at least 2 out of 3 slots of pointers used for each node. So we end up having 1, 2, 1, 2, 2 out of 3 slots for the pointers are used there without having to adjust the height. But whenever we borrow the pointers from the left sibling, make sure that this one got changed accordingly, right? Otherwise, it will not be a valid B plus tree anymore. All right. So that's the B plus tree. And tree structure index is really good for range search. And then we see later that for hash-based indexing, we cannot do the range search. Or if you attempt to do range search with hash, DBMS would just bypass it and say it knows better than you. So it's okay, we're not going to use hash for range because it's bad, something like that. And now we have known 2 structures, ISAM as a static structure, and B plus tree is a dynamic structure. If you have mostly static database with not a lot of insertion or deletion, ISAM is probably good enough. And if you have a few more insertion, we would add on overflow pages there. If it's not a lot of overflow page, it would not affect the performance that much. But if you have really dynamic database, have lots of insertion, lots of deletion going on all the time, we would go toward B plus tree or B tree. It will make sure that the tree is height balanced at all time. And well, in both cases, both ISAM and B plus tree, we have really large fan outs so that the height of the tree is relatively small comparing to binary tree. So make sure that we have only a few axes and then we get to the leaf node right away. Okay, so overall, maintaining all these structure, either ISAM or B plus tree, is better in terms of performance comparing to sorted files. Okay, and the fill factor, well, the one that we use like half full or whatever, the typical occupancy in the DBMS usually it's 67% on average or 2/3. And okay, and we have a little thing there. We see that if we keep inserting one at a time into B plus tree, it could be slow. But if you have let's say we have created database already, and then at the very end, you say, oh, let's make B plus tree structure there. What it does is it's not going to insert one by one into the structure. The DBMS would do bulk loading, that it could bulk load things into nodes like 5 at a time, or let's say if the node is 100 item, it will add 100 item at a time to make things much, much faster. Yeah. Well, we used to cover bulk loading, but well, I make it short. So yeah, if you want to know more, you can search on how to do bulk loading in B plus tree. All right. All right. So that's done for tree-based indexing. We do a little break and then we come back to hash-based indexing later. All right. 10 minutes, guys. Okay, guys, let's come back to hash-based indexing. All right, for hash-based, it's not really intuitive, so pay attention. Okay. All right, let's start with something very similar. In the tree base, we also have the static tree and dynamic tree. For hash, we also have the same thing. We have static hashing. So this is the one that you probably have learned about in data structure class, the same hash thing. Static hashing means that you have to determine number of buckets in advance. So let's say if you want 10 buckets, 100 buckets, 1,000 buckets, whatever. So that's the predefined number of buckets there. If you want to change number of buckets, you have to do like reorganization of the whole bucket thingy and yeah, all over. So that's static. Okay. And we will look today that for both static hatching and static tree, we have the same problem. Okay. So when the file grows, when you have a lot of insertion, static things, it's not enough anymore. So we have to somehow add the new buckets. But how do we do it dynamically? Okay. So for static hatching or typical hatching that you learn in like data structure class, we have something called hash function, right? The the idea of hashing is that you have buckets and the buckets are not stored things in the sorted items just like tree, because for the tree it's based on search key and then it's sorted in alphabetical order in the values whatever. But in hash, the main idea is we want to break all of those ordering. We want to make sure that everything got randomly like get into the buckets, not randomly, it's systematically based on hash function that you have. If you have good hash function, it could put things in uniformly way. So all the buckets will have typically the same amount of items. Yeah. Okay. And that's what it is for static hashing. And the key idea is hash function must be fast. So whatever search key that we put in the hash function, it will spit out the value very fast so that we know that we can jump right away to that particular bucket to get to that value. All right. So that's, well, we have data pages there, very similar to the ones that we did in tree. But in tree, everything in data pages are sorted order. But in here, no, it's not in sorted order anymore. But it's based on hash function H. Whatever search key that you put in the hash function, it will just give you the position where data page, which data page you would put your item into. Okay. And we have different types of hash function available there. And for simple ones, um, well, at the end, we have to do modulo and mod number of buckets there. Number of n should be prime, but well, it's not necessarily. Well, in reality, we could have a million um, buckets, the 2 million buckets, 10 million buckets. Well, that's fine. But the desired hash function must be uniform and random. Well, I covered that in just a little bit. Okay. For static hashing, the same with ISAM. We have problem when we have full page. So no matter how we use the hash function for, but whenever we hash something into page number 3 there, and then page 3 is full, so what we could do is we could add overflow page. And you have the same result. If we keep adding things in the overflow page, we end up with long chain of overflows. And then that would affect your searching because you have to search through the whole chain of pages. So is there a way to do that? We can reorganize all the buckets and everything once in a while for static hashing, or we can do dynamic hashing later. Okay, a little bit about notation. Sometimes when you look in the textbook, we can see that we have hash function there, and then at the end we modulo n, mod the number of hash, the buckets. But sometimes we omit the part mod in there. It's not saying that we don't have to mod the the number of buckets anymore. It's just that the modulo things got embedded into the hash function itself. Okay. Okay. The worst possible hash function would be hashing everything into one same bucket. So everything is in the same bucket. So that's no use, right? So we would hope that if we change the hash function accordingly so that it could uniformly spread things all over the buckets that we have, that would be nice, right? And also random. Well, what does it mean by uniform? That's easy to understand, right? If you have 10 buckets, it could uniformly distribute all the items into all the buckets that we have. So that's uniformly distributed. But random, it means that it should not depend on the actual distribution of the search key itself. For example, if we have 13 and 14, they should not be in the same bucket or the bucket next to each other because it should not have that type of like distribution ordering like in the hash function there. It should be randomly distributed based on the the, uh, the hash function that you have. Okay. For example, let's say we have the word Brighton. We can map like A to number one, B number two, C number three. Okay, we got stuck here with the rain. Okay. And so on. So let's say we have Brighton there. So that's Brighton there. And then we add all the numbers up. And then we get the number modulo, let's say we have 11 buckets. So modulo there, and then we get number 5 there. But let's say if we have another word called Brighto without the N at the end. Okay. So in the tree-based stuff, Brighto and Brighton would be probably in the same page because it has very similar ordering. But in here, Brighto and Brighton should be in different bucket because um, without the 14 there, it should not assign Brighto to bucket number 5 because in the random property there. But in here, this is not a good hash function either because let's say if you have like anagram, let's say cat, the word cat and CAT, ATC, whatever, if you shuffle the order, if you use the hash function this way, you get the same hash value, right? You get the same bucket. But to modify that, we can easily put the let's say the position value and multiply that there. Let's say position 1, so multiply by 1. This is multiplied by 2, 3, 4, 5, 6, 7, 8. That would resolve the anagram problem there. But the actual hash function that we use in the DBMS these days, they have some base value. Let's say some prime numbers, say 31 to power of position, power of 5, power of 4, power of 3, power of 2, power of 1, power of 0, something like that. And then multiply that with that value A to Z. That's a typical hash function that we use these days. Yeah. All right. So the point is having a good hash function would actually matter because if it's not uniform, things would get accumulated into one same buckets. That's not good because it would take more time to search through things in the bucket. All right. Okay, now this is for static hashing when we have overflow pages. Okay, usually we have overflow because we don't have enough buckets. Um, Even though everything is full, well, we need more buckets. You have to add overflow pages. And sometimes we think that we have enough buckets for everybody, but we have skews in the distribution. So somehow some buckets are really few There are really few items there, and a lot of items got like accumulated into one particular bucket. So for that part, we probably need to add more overflow buckets in some particular buckets. All right. And sometimes the hash function is not good, so that it's not uniformly distributed, whatever. So we need to add overflow bucket at the end. All right. So bucket overflow can be reduced, but it cannot be eliminated altogether. Right? This is for static hashing, typically. So, yeah, that's the problem when databases grow with a lot of insertion. So if you have like static database, hash function, that static hashing is probably good enough. But if you have dynamic database, or it keeps growing with a lot of insertion in the future, you will end up with long overflow chains of pages or buckets. Okay. So one thing that we could do is we could do periodic reorganization of the whole file and rehash everything into larger number of buckets. We could do that. But when we have a large database, reorganization or rehash the whole thing, it could take the whole night, many hours or whatever. Yeah. So we can avoid that by using something called dynamic hashing. Okay. Dynamic hashing that we use these days, we have extendable hashing and linear hashing. Okay. Before we learn about each type, let's look at the hash indices first, right? Um, it uses the same idea as the tree-based indexing, that we need to have search key. We have lots of fields there. We have to pick which search key or which attribute that we need to use as a search key. And then we use that to build your hash function accordingly. Oops. Okay, so this is an example of hash function H there. And this is my raw data, like all the data records there. And then we have buckets. Let's say I have 7 buckets total, starting from bucket 0 till bucket 6. And then let's say if I have full bucket 3, it's already full. So what I have to add is another overflow bucket here to accommodate the new items insertion there. But in all of them, it's very similar to the pages in Treebase, that we have the items and then we have the pointer that points to the actual records. The difference would be, instead of traversing the tree on top like a tree base, we have only one direction, like starting from hash function, and then it gives you the bucket number right away. So this is the the fastest thing about doing the hash, because you can get to the bucket without having to go through the non-leaf nodes and things like that. Okay, now let's start with something called extendable hashing. Okay, it's one type of dynamic hashing. Okay, this is probably the easier thing to understand comparing to the linear hashing. Okay, so let's start with extendable hashing first. The easy way to explain to you is, for extendable hashing, it has something called directory, like another in directives, like another layer of directory, and before it points to the bucket. Okay. And the bucket address, we use the binary numbers. Binary numbers. So let's say we start off with 1 bit. 1 bit can accommodate 2 buckets. If you use 2 bits, you can accommodate 4 buckets. If you have 3 bits, you can have 8 buckets and so on. Okay. The thing is, since it is dynamic hashing, so number of buckets can change dynamically. It can grow dynamically, which is not true in static hashing. In static hashing, you have to specify the number of buckets in advance, and then it stay there forever until you reorganize the whole thing and then change number of buckets later. But in dynamic hashing, it grows the number of buckets It's created as you need it. Okay. So each bucket, it's like just like a page. It stores value there with the pointer that points to the data record. If you want to locate the bucket, well, easy, just like a hash scheme that you learned in the past. You have to pick the search key, put the search key into the hash function. Hash function will give you some value. And then the value, you look at the last I bits of that number so you can know which buckets you're talking about. That's it. But if you want to insert a record, that's the same thing. We need to, just like the search, you have to find out which bucket can I insert my item into. So just like a lookup. And then if there is a room in the bucket, you add a number there and then we're done. But if there is no room, that's the problem right there. That, oh, the bucket is full. So you need to split the bucket. So very similar to the node in the tree. When the node is full, we split the node. In the bucket part, if the bucket is full, we split the bucket very similarly. Okay. And when we split the bucket, there are some things that we need to know because um, the buckets are accessed through binary number. So we use the last I bits of the value to locate the bucket. Okay. So if you want to add number of buckets, you will need more bits to access those buckets. So if, like I said, if we have only 2 bits, we can maximum have 4 buckets total. But if I add another bucket, I have 5 buckets, we cannot access 5 buckets with 2 bits. So we need to add one more bit to it into 3 bits. 3 bits can accommodate up to 8, but if I have 5, I can have 8 mapped to 5, not a problem. But I cannot map 4 to 5. Okay, so that's the whole idea of increased number of bits to access the bucket. Okay, when the bucket is full, we do the split. When we have deletion, that's the reverse of it. So we take things out of the bucket. If bucket is too lonely, it's too empty, we merge the bucket. And when we merge the bucket, sometimes we can reduce number of the directory size, and then we can use fewer number of bits. So from 3 bits, we may reduce down to 2 bits and so on, depending on how much you delete. Okay, now the situation where when the page or the bucket is full, we could actually reorganize a file by doubling number of buckets. Yeah. So what it does in extendable hashing is we have the directory. Directory has nothing. There is no search key in directory, but it's just the slots according to the number of bits. And then if we double the size of the directory, that means every time we double, that means we need one more bits to access. Like from 1 bit to 2 slots, to 2 bits, 4 slots, to 3 bits, 8 slots. And then for 4 slots, 16 slots, we have 4 bits and so on. Okay. The thing is, there will no longer be any overflow page happening in extendable hashing whatsoever. Okay. Now let's take a look at how it's done. This part is called directory. You could see that this is just a directory that points to the bucket that we have. So number here is called global depth. Global depth is number of bits that we need to be able to access each slot. So number of bits is 2. That means I use 2 bits. 2 bits, so 0, 0, 0, 1, 1, 0, and 1, 1. That means I can accommodate a total of 4 buckets maximum. So 0, 0 points to this bucket A, 0, 1, bucket B, 1, 0, bucket C, 1, 1, bucket D. And each bucket will also have a number called local depth. Local depth means that how many number of bits that we need so that things can stay in the same bucket A. So here, if local depth is 2, that means the last 2 bits for all the items in bucket A must be the same. So now if you look here, number 4, 12, 32, and 16 has a number of a last 2 bit. The last 2 bit must be 0, 0, right? For 1, 5, 21, and 13, they have 0, 1 as the last 2 bits. 1, 0, 10, we have 1, 0 as the last 2 bits, and 15, 7, and 19 has 1, 1 as the last 2 bits. So here I use only last 2 bits according to local depth that is specified. Okay. And global depth is always the maximum number of all the local depths that we have. So if I have local depth to be 2, 2, 2, 2, so global depth must be 2. So maximum of all 4 values. Okay, now here is how we could use this directory to find stuff. Let's say I want to find number whatever value of the search key. But if hash function gives me 5, number 5. So if I look at binary number 5, it's 101. So 101, if I look at the last 2 bits, according to global depth, last 2 bits, it's 1, 0, 0, 1, sorry, 0, 1. So I go to bucket B. That means number 5 must be in bucket B. Okay. And then if I want to insert something, let's say I want to insert something into bucket A or B that is already full, I have to split the node, okay? Split the node. But when I split the node, there is a problem. Because right now, my directory, for each slot, I have 1 pointer there, right? But if I split the bucket, that means from 4 to 5. I cannot have directory of 4 slots point to 5 buckets. So what I need to do is I have to reorganize the directory somehow. And the way extendable hashing does is it double the directory. So from 4, it would double to 8. And in that way, instead of having 4 slots for pointers, I end up having 8 slots. And 8 slots, we can point that to 5 buckets with no problem. Okay. We see that in just a little bit here. Okay. So let's say, look at the easiest case first. I want to insert number 6 there, 6 in there. So 6, if you look at the binary number, it's 1, 1, 0. First thing, I go to directory part. I look at the global depth. Global depth said 2. So I look at the last 2 bits, 1, 0. So 1, 0 is this one. So I want to insert 6. So 6 must be in bucket C according to the last 2 bits. So I just, if there is a space there, I just put 6 there and then we're done. So this is the easiest case. I don't have to change anything except for inserting 6 into bucket C, right? So that should be no problem. All right. Now let's take a look at something that costs doubling. If I want to insert 20, first thing I looked at global depth. Global depth says 2. So last 2 bits of 20 is 0, 0. Okay. Now look carefully. 0, 0 points to bucket A. Bucket A. So bucket A has 4, 12, 32, and 16. So, well, I just change everything to binary for you just to make it easier. So we see that if you look at the last 2 bits, they're all having 0, 0 as the last 2 bits, right? But 20 is also having 0, 0 as the last 2 bit. But I need to put 20 into bucket A, but bucket A is full. What do? I need to split the bucket, okay? Bucket B, C, and D are stay the same. I split bucket A to A2 down here, bucket A2. And to distribute items from bucket A. So I have 4, 12, 32, 16, and 20. There are 5 items. I have to spread them across bucket A and A2. How do I do that? If I only use the last 2 bits, I can't really do that because, well, my directory is only having only one pointer that points to bucket A. But right now I have nothing points to bucket A2. So what I need to do is I need to double the directory. Okay, double directory. So if you look at the structure, you see the structure that we had before, 0, 0, 0, 1, 1, 0, 1, 1. Every time we double, we just add zeros and ones in each of the structure that we had previously. Okay, so let's say if I want to double this 8 slots again, I just put 0 in front of all 8 items plus another 8 with 1 in the front. Okay, that's called doubling. When I double, that means that global depth would be increased by 1 because I will need to use more than 2 bits to have all the pointers available. So with 2 bits, I only have 4 buckets. But if I double them to 8, I have 8 pointers. Okay. But since bucket B, C, and D's are, they have no problem, right? So you could see that bucket B would have 2 pointers pointing to them. Bucket B also have 2 pointers. So here, if you look at the structure, that's 0, 1 and 0, 1. There, 0, 1, 0, 1. Even though the third, the last third, well, 3 bits from the end is 0 and 1. Well, that doesn't matter, but both of them points to the same bucket B. For bucket C, that's the same thing. 1, 0, 1, 0. They both point to bucket C. Bucket D also have 2 pointers point to them. But the problem is, well, with bucket A, this is what we want. We need some pointer that points to bucket A too. So to be able to do that, we have to increase the local depth by 1. From 2, we have to increase to 3. So now instead of using the last 2 bits, I need to use the last 3 bits. So now back here, the last 3 bits of 20, that's 1, 0, 0, 1, 0, 0, 1, 0, 0. So 24 and 12 must be in bucket A2 with 1, 0, 0. And the other ones, the last 3 bits are 0, 0. So 32 and 16 must be in bucket A. So bucket A will be identified by the last 3 bits, which are 0, 0, 0. Bucket A2 is accessible by 1, 0, 0. Okay, so without increasing the local depth to 3, we have no way of having extra pointers that could point to bucket A2 for you. Okay, so for here, even though we have 8 slots total, we can always point to something less than 8, right? So 8.25, that's fine. For splitting bucket A to A2, we increase number of bits so that we can distinguish between items in bucket A with 0, 0, 0 or bucket A2 as 1, 0, 0 as the last 3 bits. Okay, the rest of the buckets stay the same. So in here, we can actually insert number 20 into my buckets with 1 bucket added into the system. Only 1 bucket, okay? But the directory got double, but the size of the directory is really small. So doubling the directory doesn't, well, it doesn't cause a lot of problem because of the smaller size. Okay, so here this is the explanation of what we're talking about, that originally if we only use last 2 bits to identify the bucket, but if we split the buckets, we need more pointers to point to, so we need 1 more bits. If we start off with 5 bits we have to add to the last 6 bit and so on. Okay. And once we change the local depth, the global depth must be changed accordingly because the global depth is always the maximum of all the local depth that we have. Now, local depths, we have 3, 2, 2, 2, 3. So maximum is 3. So global depth is 3, which matches all the bits that we need to create directory of size 8. All right. So for extendable hashing, the growth of directory is always double. We never have directory of size 5, size 7, size 13. Never. We either see 2, 4, 8, 16, 32, 64, like that. That's a directory. But the actual number of buckets, well, we can have any number. Okay. All right. And if we want to delete something, if we delete something, the bucket could be empty. We can, let's say, if we split the bucket into A and A2, and let's say we keep deleting things out of A2. So A2 is too empty. So we could merge A and A2 back together. Once we merge back, oh, we don't need that many bits anymore. So last 3 bits got reduced down to last 2 bits, and then directory got half the size. So it's like in the reverse way for deletion. All right. So here directory grows in spurts because it goes like double, 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 double. But the bucket number can grow one by one depending on how much you need to split. Okay. Okay. And the benefit of external hatching is, well, it's dynamically the the bucket size grows dynamically with the need of insertion when you want to insert something into your buckets, and it reduces down the number of buckets if we don't need them anymore. Okay, and space overhead is really small because we have like the directory part, but directory is not large in size. Disadvantage of external hatching, because we have extra level of indirection. That's the directory that we're talking about. And the bucket address table could be very big if we have really, really large number of buckets. So sometimes you need to have some tree structure to on top of the hash structure as well. All right. And if we somehow need to change the bucket address table, it's expensive operation. But usually the DBMS will probably determine that for you, help determine that. So we have another scheme called linear hashing. It also is dynamic, but since XML hashing has some disadvantage, so linear hashing comes in and tries to reduce down some of its disadvantage of XML hashing. But there's a cost. It will have some bucket overflow happening in linear hashing somehow. We'll see that in just a little bit. But before we move on to linear hashing, let's look at more examples just to make sure that you understand how extendable hashing works. So let's say we start out with the things on the left with 5 buckets right now. We have a directory size of 8 slots using 3 bits. That's a global depth, 3 bits. If I want to insert 68 there, okay, first thing, I look at the global depth, 3. So that means I have to look at the last 3 bits of number 68. So that's 100. So 100 is right here. It directs me to bucket A2. So if I want to insert 68 in here, bucket A2 is already full. So what do? I need to split the bucket. Okay. So whenever I need to split bucket, I need to increase the number of local depth because right now bucket A2 is 100. And if I split into another bucket, since there is no overflow page allowed, so I would need more pointers that could point to my splitted bucket. Okay, now I need to distribute the bucket. Okay, I have split into bucket A3, A2 and A3, and I need to redistribute the items 4, 20, 36, 12, and 68. So if I look at the old values, we have 4, 12, 20, 36. They all have the last three bits of 100, right? 68 is also have 100. But if I split the bucket, I have to look at the last four bits, the last four bits. So number 4, 20, 36, 68 have the last four bit of 0, 1, 0, 0. So they would be in the same bucket. So 4, 20, 36, 68 in the same bucket because it uses 0, 1, 0, 0. There, 0, 1, 0, 0. Bucket A3 has 1, 1, 0, 0. So that's bucket A3. But originally with only global depth 3, we cannot get to the last four bits. So we have to double the directory. By now, instead of using last three bits, I have to use 4 bits there. So if you look at the structure there, you have 0, 0 until 1, 1, 1 there. And then you add 0 in the front. And then here, another substructure there, and you add 1 to the left. So that would definitely double the structure for you. All right. But now, if you look at buckets B, C, and D, how many pointers do we have? 4 pointers. Well, that's because we have skewed structure that um, we keep trying to insert something into bucket A. Keep doing that. And B, C, D got so lonely. So we have a lot of pointers that points there. Because why? Because bucket B has local depth of 2. So if you look at all 4 items here, that's 1, 0, 0, 1, 0, 1, 0, 1, 0, 1. They all have the last 2 bits the same as 0, 1. That's why all 4 of them points to the same bucket B. Okay, the same thing with bucket C. The last 2 bits is 1, 0. So you have 1, 0, 1, 0, 1, 0, 1, 0. And all 4 of them points to bucket C and so on. But for A, now, if you look at bucket A, now we have 2 pointers point to bucket A because the local depth is 3. So we look at the last 3 bits. We have 0, 0, 0, and this one 0, 0, 0. Last 3 bits the same for 64 and 16. That's why we have 2 pointers points to bucket A. But in bucket A2 and A3, that's different because we have local depth of 4. So we need last 4 bits. That's why we have only 1 pointers per bucket there. Okay, got it? Now, another example, we want to insert 69. So first thing, we look at the global depth to know how many bits we need. We need the last 3 bits, 101. So 101, we go there. That's 101, bucket B. And then we want to insert 69 there. The bucket B is full, so we need to split the node. Okay, but now splitting the node is easier this time. We don't need to double the directory. Why? Because right now we have 2 pointers point to bucket B. So if we split the bucket, we can split the pointers, right? That would be easy. But the way we split the bucket, we do it by we increase the local depth number from 2 to 3. That's all you need to do. And we redistribute the items. We have 1, 5, 21, 17, and also 69 we want to insert. Starting from last 2 bits, now we increase to last 3 bits. So now we can differentiate the buckets from the last 3 bits. 001 would be number 1 and 17 in 001. And in 101, we have 69, 5, and 21 in bucket B2. Okay, so we differentiate them because the last 3 bits are different there. Okay. So here we could see that we can have bucket splitting, but the directory stay the same. We don't need to double directory all the time, because this one we don't need to, because we have available pointers for the splitting bucket. Now we want to delete something. If I want to delete 16, first I look at a global depth of 3. So look at the last 3 bits so I can locate the item. 16 must be in bucket A. And okay, delete 16 away. And then what would happen? If I want to merge the bucket, the easy way to do is I have to decrease the local depth from 3 to 2. So if I decrease the depth, the local depth to 2, that means I can locate the bucket by using only the last 2 bits, which are 0, 0. We have 0, 0 here and 0, 0 here. That means if I want to merge a bucket, it will be this bucket, bucket A2. And if I merge them, I would decrease this one from 3 to 2, from 3 to 2, and I merge them together. Okay. When you merge, you decrease this down. Once you decrease it, global depth would decrease accordingly, because global depth is always the maximum of all the local depth that I have. Local depth right now, they're all 2. So global depth must be 2 as well. So when global depth is 2, that means I cannot accommodate 8 slots anymore. I can only do 4. So I halve the directory size. Yeah, this time. And when I have them, there will be no problem, because for each one, there are 2 pointers pointing to each bucket anyway. So that's already an extra ones. So when I halve the directory, well, we only have 1 per bucket, which is enough for 4 buckets that we have. Okay. And another example, I delete 10. So start looking at the global depth 3. So 0, 1, 0. 0, 1, 0 is this bucket C. Okay, and I want to delete this one away. But what would happen when I delete this thing? I cannot have the directory size. I cannot merge the bucket because I don't have anywhere to go, because everybody else is still, well, there's no place that I could merge the bucket, because if I merge the bucket, I have to merge with the last 1 bit, which is not possible because we also have 4 other buckets out there. So we cannot merge the bucket this way. So we can leave it as like a placeholder, like empty space like this, because we cannot merge. All right, so that's a case where we can delete and merge the bucket, and some case where we just cannot merge. Okay, so that is the extended hashing. Now, linear hashing is another scheme. For linear hashing, it sort of handle long overflow chain without using directory, but it will have some overflow pages. In exponential hashing, there is no overflow page whatsoever, nothing, because we split the bucket. But in linear hashing, there will be overflow chain, but it would not have many long overflow chain, because that's a problem if you have long chain. But if you have a few overflow chains, well, that's not a big of a problem. Okay. Now, the idea is very similar. We also use the last I bits of number as a level of splitting. No, not splitting. Yeah, we do splitting. Okay. But if you sleep, wake up. Now, this is the important one. When we do bucket splitting, in external hashing, we split when we need it. Like let's say bucket A is full, we need more space, we split the bucket into A2. When bucket B is full, when we need some space, we split the bucket into B2, whatever. But in linear hashing, it's different, really different. When we split, we do not split the bucket that we want the space. This is weird, but this is how it's done. We split round robin. Do you know what round robin means? Well, we split when in the cyclic order it needs to split in the some particular order. We do not split because we need to split that bucket. We split, okay, we need to split, but split what? Okay, what's in the list? What's next? We split that one, even though that's not the full bucket. That's fine. Okay, this is the main difference. Linear hatching, we split the bucket, but we split the bucket in round robin way. Okay, and splitting proceeds in rounds. When the round ends, we restart, reset the splitting all over again. Okay, and they use the word level for current round number. It doesn't really matter because um, doesn't really matter much. Yeah. The important part is we allowed overflow pages or overflow bucket to happen. And when we need to split, we split in round robin fashion. Okay, now let's recap a little bit. We've seen that in external hatching, when this bucket is full, and let's say you want to insert 20 there, when there is no space left, we split the bucket and then we redistribute the items with increased number of local depth. Okay. But before, we could have something like overflow bucket like this. So when the bucket is full, if we do not split the bucket, we can add an overflow bucket and add something there with the same local depth. Not a problem. Okay. And once we have overflow, like let's say we allow this to happen. Okay. And when it's time, well, the round robins, when it comes to its turn and we split this one, we could split this and break the chain and make it two buckets like this. And now we can increase the local depth accordingly. So that would be the similar way. But eventually, its time will come and it will break the overflow chain somehow. And then it got split like that. Okay. Now a big overview of LHS linear hatching. Okay. In the middle of the round, let's say we start off with, this is what we start off with this many number of buckets. And then we split, when we split this one would appear. When this one got split, this one would appear. Round robin is in order. And then next time we split this one would appear. Split this one would appear. Keep on going. We keep splitting. And then this one would keep growing, right? When we hit the end of the round, that means we will, at that point, we will double the size already, right? We keep adding one at a time. But when we're done with that current level, we would end up with doubling the size. But at this point, we will not go further. And then, okay, we're done with this round and we got double in size. And then we reset, start over again. But now I have a bigger size to start off with. And we keep on going the next round. Okay, this is the main difference between linear hashing and extendable hashing. Okay, we just keep on going, split one at a time, but it may or may not be the one that is full, but keep going. And then eventually everybody get to split with the same amount of amount of splitting. So here, the light blue part is the original buckets to start off with. And then we keep splitting. Let's say we split 1, 2, 3, 4, 5. So we would have 5 more items that we already split there. We keep on going. We keep on going until we hit the end of the original data. Once we hit the original of the data, that means we will actually double the size of the number of buckets that we split, right? If we have 20 of this, at the end of the round, we will also have 20 of this, right? Okay. And then when we're done, we will reset. And now in the next round, this will be my original data. So see, this one get bigger. And then I start over, splitting this one to get this one. Split this one, get this one, and so on. And then I will end this round when I hit this particular bucket. And when I hit this one, I actually double the size of the bucket. And then I reset with the bigger size and keep on going. All right. Okay. Now, when do I split? In external hatching, the trigger to split is when the bucket is full. Like I want to insert something into a full bucket and that trigger to split. But actually, there are other triggers to split for linear hatching. The typical ones will be when explain linear hatching splitting with round robin. Okay. In round robin way, we do not care whether the bucket is full or not full. In external hatching, it is when the bucket is full, we need to split that particular bucket that is full so that we don't have the overflow, but we have extra bucket to distribute all the items there. So that's the trigger for external hatching split. But for linear hatching, it's not that way. We could have some type of trigger to split, but when we split, we will ask, where am I right now in the splitting process? If I am right now is right here, so the next time that I need to split, I will split the next one. I don't care if that bucket is full or not full. I don't care. But when it's time to split, I have to split the next one. And then when this one got split, I have this. And next time around, I would get the next one to split. I don't care if it's full or not full. When it's time to split, I ask where where is my current cursor to split. If it says right here, I will split that one. I don't care about the content. I don't care if it's full or not full. I just split in round robin way. Round robin means it goes in order, no matter what. Okay, so the trigger to split could be something different. It could be that when I want to insert something and the bucket is full, that could trigger the split. But the split may not happen at that bucket. It was split somewhere else. Well, that's fine. That's also the trigger to split. Or in some DBMS, they would use the load factor. If my load factor hit that particular number, I would trigger the split. The load factor means like when I have this many items in my buckets in my whole database. Like, yeah. Yeah. Very many different ways, but I guess the easiest way that we could use for this class, we can use the trigger as when I see the full bucket and I need overflow. When anytime I need to create an overflow page, that would trigger the split. But trigger the split where? I don't know. I'd look at the cursor, my current cursor. Okay. Now, since the split is in round robin way and overflow page is allowed, how would we break the overflow? Because we allow them to happen, but eventually, since it's in round robin, eventually it would get its turn to split somehow, some way, sometime. When it gets to its turn to split, it will break the overflow that time. Okay. So overall, the long overflow chain will not develop. I'm not saying that it would not have any overflow because we allow overflow. And sometimes we cannot break or like melt down all the overflow altogether. It may reduce down from overflow of 6 buckets down to 2 overflow, something like that. And at the end, after rounds and rounds of splitting, eventually overflow would get broken down. Yeah. So um, doubling in directory, doubling a directory in XML hashing is very similar to let's splitting in linear hashing. After one round, one full round, you are actually doubling the size. So that's the same thing, but XML hashing, where we keep the directory and we keep doubling at every time. Okay, now let's take a look at example of linear hashing. The basics are the same as XML hashing. We use the last 2 bits, last 3 bits, whatever, last I bits of values. So here, if we have primary pages of 4 pages or 4 buckets, we need 2 bits, right? 2 bits. So we have 0, 0, 0, 1, 1, 0, and 1, 1. The way we put things into the buckets is the same as before. We put in a hash function, and then hash function will tell you which bucket it belongs to. And let's say in here, if we keep adding stuff into, let's say, if we want to insert something into this bucket, say I want to insert 43 here. I want to insert 43. So what would happen? It will look at my hash value. 43, let's say, turns out into bucket 1, 1. So I say, I have to put 43 into this bucket, but this bucket is full. What do? I trigger the split. Okay, trigger the split, but where do I split? Okay, look, 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 look. We're not splitting this one. We're not splitting this one. I haven't split anything before. So the first one would be, this is my cursor, right? My next one that I need to split. So I would split this one. Even though it's not full, I don't care. It's time to split the first one. Let's split the first one. So I split this one into this one. And then I redistribute the items as before, just like extreme hashing. I look at 32, 44, 36, but instead of looking at the last 2 bits, I need to look at the last 3 bits now. Otherwise, I would not be able to differentiate between these 2 buckets, right? So now, if you look at the last 3 bits, we see that 32 has the last 3 bit of 0, 0, 0, and 44 and 36 has the last 3 bits of 1, 0, 0. Okay, so now I redistribute the item even though bucket 00 is not full. But it's time to split the first one. So let's split the first one. What triggered a split? This overflow. This overflow triggered a split. Okay. All right. And then if I keep splitting, and you could see that the next cursor keep on advancing. So when I split this one, next goes to the next one. So when it's time to split the next one in a row, so I need to split this one and keep on going. So at the end of the round, let's say this is my time to split. You could see that this overflow did not get resolved after three splits later, right? So you keep splitting this one into this and this, splitting this one into this and this. And then next time around, when we have overflow, let's say this overflow, trigger the split. When do I split? When do I split? Oh, I split here. So it breaks the overflow chain. So it redistribute 31, 35, 7, 11, and 43 into these two. And then because it's the end of the round already, the end of the original round, so we reset this thing back to the beginning. And now the next round would contain 8 items to split. And then we keep splitting 8 times. When we split to the 8th time, we reset the next to 0 again. You could see that this time around, even though 43 got into overflow bucket for a long time. Eventually, it gets its turn to split, and then it broke the overflow eventually. All right. So that's what linear hatching is about. They're very similar, but we have different like directives a little bit. So for extended hatching, we have directory, and then we double directory each time, but the number of buckets grow one by one, depending on like the need. When we need to split, we split. In linear hatching, it's a little different. We do not maintain the directory, but at the end, things go in. Um, we have to double the things after one round is done anyway. But the rest of distribute things across buckets are very similar using the last I bits of numbers. If you want to have more resolution, you increase number of bits by one. Okay, so if you compare between tree indexing and hashing, well, most of the time when you want to pick whether or not you want to use hash or tree, mostly because of the search. If you want to do equality search, you already know from the data structure class, right? If it's like equality search, hash is the best. The best is really fast. But if it's range search, hash is worse to the worst to the worst, right? So when you're not sure whether or not in the future we're gonna do range search or not, it could possibly be having some range search in the future. You would not assign hash to that. Okay. So if we have equality search, go with hash. The rest, we can go safely with tree-based indexing. All right, so that would cover everything as introduction to indexing. So we will pause on indexing a little bit. Next time we will do milestone 3. And the week after that, we'll come back to indexing again. And we are going to do the cost analysis of all the scan, all the insert, delete, and then we see different structures will have different costs. So we will understand it better. So when we use, pick what to use for your database, you would pick it more wisely. All right. So that will be for today. Um, yeah.